Hello, this is Leo from CCS America. In this section, I would like to talk about some lighting technique for line scan application. Before we talk about the lighting technique, at the beginning, I want to spend some time to talk about what is line scan application and what is line scan camera. Here is the comparison between the area scan camera and the line scan camera. The first and the major difference is the sensor. For the area scan camera, the sensor is array of pixels. So there's horizontal and vertical. And when it captures the image, it will capture the whole field of view at one shot. On the other hand, for line scan camera, the sensor is one single line of pixel. And every time when it capture, it will only capture one row pixel. There is some multi-line line scan camera too, but the purpose for that is mainly just to increase intensity. So the principle will be the same. So for line scan sensor to cover the whole field of view, it will need to keep scanning one row by one row, which means they will need to have some relative movement between the sample and the camera. Most of the case, the sample is moving, and then the line scan camera can scan one row by one row, and then at the end, it will combine all the rows and create a complete image for the full field of view. An area scan sensor usually is smaller, so the lens mount for it is also for some smaller mount, like a C mount and sometimes F mount. And line scan sensor usually is bigger, so the lens mount will also be some big one, like a F mount or M72 mount. There is also some difference on the pixel. In area scan, since it's an array of pixels, it usually will be horizontal by the vertical. For example, a 2 mega area scan camera, that means there was 1600 pixels in the horizontal and 1200 pixels in the vertical. On the other hand, line scan camera we only have the one line pixel. So AK, that only means the horizontal. And the vertical is depends how many lines you scan. So now we know the difference between the line scan and area scan. So next step, let's see what is the benefit of line scan camera and when should we use them. The benefit is actually connecting to the difference too. First, since the camera is continuous scanning line by line, line scan camera is really good for the continuous object. For example, some continuous sheet like some plastic film. And the other benefit is the high resolution. So the typical line scan camera is like a 8K, 12K or 16K. And in compare, area scan camera, the most common one is 2 mega, 5 mega, and if we look at the horizontal of this resolution, 2 mega only have 1.6K in the horizontal, and 5 mega only have 2.5K in horizontal. So compared to 8K, 12K, 60K is much more low resolution. It does have some 12 mega or 25 mega area scan camera coming out recently. But even we go to 12 mega area scan camera, the horizontal pixel is still only 4K. So compared to 16K, that's still considerable low resolution. These two benefits also connect to the typical application we use line scan. The first is the continuous sheet, like a web, transparent film, and also some paper. The other typical sample will be the cylindrical object. So for the cylindrical object, we can rotate the cylindrical object, and then the line scan camera can continue scanning the surrounding surface. And line scan is also really good at for some continuous product on conveyor. For example, in food industry will be like some bean, coffee bean is coming out from conveyor continuously. So this first application to the third one are all because of the benefit the line scan can scan continuously line by line. And the last application will be the high resolution. So if it's some application we just need to have some ultra high resolution, for example some wafer inspection, we also consider use line scan camera too. But anything have both sides. This is the advantage of the line scan, but line scan also have some disadvantage. One disadvantage is really obvious, is the high cost. Usually line scan camera and line scan light will be more expensive than area scan. And the other more important disadvantage will be the complexity. For area scan, when we do the evaluation, it's quite simple. We just need to have a camera stand, and then we can just begin to test the light. But for line scan, when we do the evaluation or when we set up the machine, it will be more complex. We need to first make sure there's a relative movement between the camera and sample, and also the movement speed need to synchronize to the scan rate. In below, there is some example when the scan rate is not matching the moving speed. If the scan rate is too slow, we get a distort image. If the scan rate is too far, we still get a distort image. So it's not like you can use your hand and manually move the sample to take the image with line scan. And also, due to the complexity for the evaluation, we commonly see people only using the very simple line scan light line for the line scan application. And then we got some very bad image, and there's no good contrast, very noisy background, and we used that image for image processing. We didn't get a stable or the good result at the end. So the main purpose for today's presentation is really line scan application, and line scan light is just the same as area scan. There is a lot of lighting technique can help us to increase the contrast, remove the background noise, and get a stable and good contrast image. So in the next section, we're going to go over 6 common line scan lighting technique. The first one, this is probably the most common line scan setup, is the floor light. It usually will work really well when the surface condition is relatively simple. There is not too much roughness or texture. And when we use the floor light, we can set it at both bright field and the dark field. In the bright field setup, if the camera is vertical looking down, the light will come from a very high angle. And for the background, the direct reflection will go into the camera and become bright. And only where there is some defect, it will become dark. Depends on the surface condition. Sometimes we will need to tilt the camera to create a V-shaped configuration, but that's also considered as a bright field. On the other hand, for the dark field setup, if the camera is still looking down, the light will come from a deep low angle. So for the background, the direct reflection will not go into the camera, so all the background will be dark, and where there's a defect, it will become bright. So this is a very typical setup. It works well when the sample is not so complex, and also the defect is some generic defect. For this type of setup, what do we need for the lighting? The first thing is the high illuminance. Since we are looking at the reflection coming from the sample, so we did need a high intensity, high illuminance. And also, usually there is a relatively long working distance, and we will need to have some optical system to focus the light, and then we can create a very focused light beam on the surface sample surface to create a bright image. As an example, the standard front light for CCS will be RSP2. So in this light, we have an integrated cylindrical lens, which will create a parallel light beam. So it can work, it's really flexible for the walking distance. We can use it in the short walking distance, but also in the long walking distance, but still get the good intensity. And also it's really high power light, so you can get very good illuminance on the target surface or the sample surface. This is the first lighting setup or lighting technique. The next common lighting setup will be a backlight. The backlight is really ideal for inspect some defect and foreign material for some transparent sample, like a transparent film or like a glass. And the series is pretty simple. Usually we put the camera on top, and then we have the sample, the transparent sample in between, below it, and then we have the backlight underneath. And if there's no defect, the light will just pass through the transparent sample and reach the camera and become bright. Only when there's a defect, it will block the light and become dark. So for this setup, we will need the light be very uniform. Since the camera is directly looking at the emitting surface, in most of the case, the intensity is not so critical. The most important thing is the uniformity. If there's a slight unevenness on the emitting surface, it will show up in the image. So we need to have a very uniform emitting surface. And also, not like the front light, we need to focus the light beam on the sample surface. Since the camera is directly pointing to the light, we just need a high luminance on the emitting surface. As an example, the standard backlight light will be LNSD in CCS. So not like the front light, there is no optical to focus the light. Instead, there is a reflection chamber. So the light will reflect inside this chamber here and there to create a very high uniform and high luminance emitting surface, which is really ideal for the backlight setting. Let's keep going. The next common lighting setup will be a on-axis or coaxial setup. This setup will work really well for the sample that have some 3D structure. For example, here is a PCB. On the PCB, there is some tall components and also have some short components. And if we use the traditional or the standard front light configuration, because the light and the camera have some angle, we cannot see this gap. But if we use coaxial and on-axis, the on-axis means the light and the camera are in the same axis, so from top to bottom. In this case, we can see inside the gap and we can get a very good image here. Actually, not only the gap, if we once we have a tall sample and we have an angle for the light or camera, we will create some shadow on one side of the top component. So for all the samples that have a 3D structure, normal front light is not going to work well. We create a lot of noise. We will need to go with the on-axis. Another very typical application beside the electronic PCB will be glass. Usually glass have some thickness, and if there's a defect on the glass, if we tilt the camera until the light, the defect will reflect on the top layer and the bottom layer of the glass and create some ghost image. So one defect will become a lot of defects, which is really not ideal. And on axis configuration, where the camera and the light are in the same axis from top to bottom, will not have the ghost image. Typical application for this coaxial setup or an on-axis setup will be electronic or glass. So the requirement for the coaxial light, the first two is the same as a front light. but there's two more requests. The first most critical is the on-axis optic. Usually what we need is a half mirror or beam splitter. So you can see here we have the normal front light, and then we have a half mirror in front of the light. So when the light coming out from the light, half of the light will reflect, half of the light will go through. We are not using the light go through, so the light will reflect, go down, and reflect on the sample and go back. Half of the light will go through and reach the camera. So from the camera point of view, we can see the light is coming from top to bottom. So both the light and camera are on the same axis. So that's the first request. Another additional request is the high uniformity, especially for the glass sample, because the surface is really specular. We will see the surface unevenness of the light. So we also need to have a high uniformity on the emitting surface. For CCS, our standard Correctional Light will be the front light NSP with a correctional unit. It's like an adapter which can attach onto the standard front light NSP2 and then create a correctional light. And when we design the NSP2, we design the light to have high illuminance, but also have a good enough uniformity, so this light can be used as a correctional light too. That's the third common lighting setup. The fourth lighting setup will be the tunnel light setting. So this light, or this lighting technique, will be really good at some sample that have rough or wrinkled surface. For example, here we have a cell phone. We have some button on the cell phone, and the button have some convex, so we have some bump. If we use a traditional front light, because the light comes from one angle, we will create some shadow on one side of the button, so we cannot get a clear image. So for this type of sample, we will need a cloudy day image. That basic idea is we have the light coming from all different angles. In this case, we can cover the surface unevenness. Since we have the light from low angle and high angle, we can get a very uniform image. So the typical application is really the sample that have the 3D structure or have some rough and wrinkled surface. For example, electronic PCB, and also some in food industry would be some like coffee bean, or all the kinds of beans. Since the surface is round shape, we do need a cloudy day light to have the light come from all different angles to remove the surface unevenness. So the requirement for the tunnel light or this type of technique is we will have the LED on the bottom and facing up, and there is a reflection shell on top. So the light coming out from LED and will get reflect on this shell and then reach the sample. So from the sample point of view, there is light come from all different direction. So that's the major requirement for this light. And the other thing is for the intensity. Because the light needs to get reflection from the dome shell and then reach the sample, it does lose a lot of intensity. And this because it's diffuse light, it also needs a lot of intensity. So we do need to put a lot of LED and very high power, very high current to get enough power for this kind of tunnel light. For the CCS standard tunnel light, we have two series, LNEAA and LNEBA. The major difference is the diameter of the tunnel. So the LNEAA is 50 mm diameter. The benefit of the small diameter is it gets higher intensity because the light will less scatter. And then the LNEBA have a 100 mm diameter. And the benefit for the bigger diameter is can cover the uneven surface better, which means get a better uniformity. So we can choose whether we need a high intensity or we need a high uniformity, or if the sample is really rough, we will go with the bigger diameter tunnel light. Until here, we talk about 4 standard lighting setup or lighting technique, which is flow light, that include the bright field, dark field, backlight, coaxial or on-axis light, and then the tunnel light setup. We have 2 more lighting technique, but these two lighting technique, I would say, is really specific for some particular application. Let's see the first one. So this time, let's first see what is the application, and then we will bring up what light do we need. In line scan application, there was one application is really difficult, traditionally really difficult. That's the scratches along the moving direction. This scratch is really common when the sample or the part is transported by roller, for example, some transparency film. And if some foreign material is fall on the roller, and when the rollers keep rolling, it will just continue to create some scratches on the film, and that scratches will always parallel to the moving direction. So for the traditional lighting method, we will use a flow light, and let's see what kind of result we will get. Now we have a film here, we have a scratches which is along the moving direction from the left to right, and we have a camera here, and we have a light of standard flow light here. And the light coming out from the standard flow line scan light will be straight, which means it will be parallel to the scratches. So it won't reflect on the scratches surface, and we will not highlight under the camera. So if we look at the image, the moving direction is from bottom to top. They're supposed to have some scratch here, but it's completely disappeared because the light and the scratch is in the same direction. In order to solve this type of difficult application, we develop a new light called cross angle light or bidirectional angle light. So here's the comparison. The traditional illumination, traditional flow light, the light is going straight out, but for the bidirectional angle light, the light is come with an angle. So one is come from the one side low angle and the other side low angle, so it's close. The benefit of this one is for the traditional illumination, because the light coming straight, it will become parallel to the scratches, and that's why we cannot see the scratches. But for the bidirectional angle light, because the light comes with a deep angle from 2 directions, so it will hit the scratches surface and then will be picked up by the camera. So you can see this is the image. If we're using the bidirectional angle light, we can see the scratches clearly. And the standard bidirectional angle light in CCS called LNIS. This light again is really specific for the for just one application. That's the scratch inspection along the moving direction. But just because this type of application is so common, it becomes really useful. The typical application, most of them is just some sample that on the roller. For example, transparent film. There's a lot of different transparency film, like polarizer film, color film, and all that type of film can use potentially use this bidirectional angle light LNIS. And also the sheet metal, that also will be another very good application. And also sometimes the glass, we also need to inspect some scratch defects. So that's the bidirectional angle light. And let's see the last lighting technique. This is also a very specific application. It's also quite common. The basic concept is really similar. It's the defect along the moving direction. But this time, the sample or the parts, it's not smooth. It's not like a transparent film, or it's not like a sheet metal. It's not smooth surface. Instead, it's a very rough surface. And this rough surface parts on the roller, it will create some stripe on the moving direction. So here I have it on sample. Above one is some paper. The below one is fabric. And if we use the traditional light source, because the light coming straight, even there is some stripe, it won't show up. And also we cannot use the bidirectional light here because we have light from left or also from the right. So these two lights will overlap each other and remove the defect. What we need is we will need to have a light come from one direction. So if there is some stripe, some dent on the sample, it will create a shadow on one side. So for example here, because the light comes from very deep angle, we can create a shadow on the left side. So also for solving this kind of application, we come up with a single direction angle light, LNDG. So not like the bidirectional angle light, we have the light come from two directions. This light is only come from one direction. So it's ideal to inspect the dent or stripe defect on the moving direction for some paper, cardboard, that type of diffuse surface. That's all for the lighting technique. Very quick summary. We talk about 6 different lighting techniques. The first one is front light, which including bright field, dark field, and then the backlight, correctional light, tunnel light, and then we also introduce 2 very specific lighting techniques. One is the bidirectional angle light, the other is single directional angle light. There's actually a lot of there's more lighting technique in line scan, but we're not going to cover everything today. But the main purpose I want to show is in line scan application is the same as area scan. We have a lot of different technique or different light source which can help us to increase the contrast and make the whole project smoothly and successfully. But they also bring up another big problem is how to do the evaluation. At the beginning, we already discussed for the line scan application, it's a little bit hard for the evaluation. We need to have some movement to synchronize the moving speed to the scan rate and all that kind of hassle. To solve this issue, CCS America recently set up a complete line scan testing station. So in the next section, we're going to show our line testing station and see how can this test station help selecting line scan light. This is the line scan testing station we just talked about. When we design this line scan testing station, the basic concept is we want to make it flexible. We want to make sure this line scan testing station can handle most of the major line scan application. On the left side is for the lighting. We can swap out for different light and we can change the angle for the bright field, dark field. It's also really flexible for different working distance. We can also put the light underneath to get the backlight result. And the right side is for the camera. It's also very universal. We can swap the camera for different resolution, different scan rate, and also for color imaging. And the last portion is the motion control. We have a motor which we can synchronize the moving speed to the scan rate to make sure we get the stable image. Let's see a real example how we're going to use this line scan testing station. Here I have a real sample. It is a PCB, so you can see there's a lot of tall components and short components, so which means it's a very 3D structure. And also there's a lot of solder ball on this PCB, and the surface is really rough. And let's see what image can we get with a traditional or the standard flown line scan light. Before the video clip, we already set up the best working distance, and already set up the line speed and the scan rate, everything synchronized, so it looks really smooth. But in the real world, we will take a lot of time to do the calibration. So let's start the motor and then capture image. Here you can see this is the image we can get with a standard flown light. First, we get a lot of shadow on one side of the tall component, exactly as what we expect. We already discussed that in the last section. And also, if we focus on the solder board, we can see we only cover half portion of the solder board, and the other portion is completely dark. So definitely, the standard flown light is not going to work for this type of application. As what we discussed in the last section, for this kind of sample that have a rough surface and 3D structure, the best lighting solution will be a tunnel light. So here is our standard tunnel light, LNEBA, and let's see what image can we get from this light. Again, I already set up the best working distance and everything before the video taking, so it looks really smooth. But when we do the testing, we will need to test all different working distance to find the best configuration. But let's save it for this video taking. So now we have the tunnel light on, and let's begin to take an image. Here is the image we can get with the tunnel light. You can see we get a clear coverage all around the tall sample. There's no shadow. And also, if we focus on the solder ball area, we get a clear coverage all around the solder ball. This is definitely a much better image compared to a flown light. And I will say this is the best optimized solution for this PCB inspection application. In conclusion, line scan application is typically more difficult than the area scan application when doing evaluation. And we're really exciting to have this capability, to have this line scan testing station. We invite you to take advantage on our line scan testing station to help solve your line scan application. Thank you very much.